Hello and welcome to NPTEL MOOC on Applied Electromagnetics for Engineers. In this module we will briefly recall coordinate systems, and to introduce coordinate system let me ask you by a question. Let me begin by asking you a question. Suppose you have a long road, okay, the road stretches all the way from minus infinity to plus infinity. Well, I gave away the game a little bit, but anyway, so there is a long road, okay. On this road there are houses which are spreading all over the road, and these houses are kept at a certain distance. So you have your house, then you have a next house, next house, next house, another house beside you, and so on, okay. Suppose you want to invite your friend to lunch on a particular day. How do you go about inviting your friend? Let's say you can call up your friend. Each friend has a phone, so you can call up your friend and invite this person to lunch, okay. Remember, it's a long road. There is nothing to distinguish your house from your friend's house or your house from a different house. So how do you go about inviting your friend? You might try a simple idea. You might say that, well, I know which house I am in, so I'm going to call my house as the reference house, okay, and then I count the house in which my friend lives and then pick up a phone, tell him or her that I am at the reference house, please come. However, the friend would immediately say, well, no, I am actually at the reference home, because one reference point could be as good as any other reference point in a infinitely long road, right? So any point could be reference. So therefore these two friends do not even agree upon which one is the reference road. On the other hand, you could say something like this. You can say, okay, I am going to make my house as a reference house, but I am going to put a number to my house, okay. I am going to say a number 0. Let's say my friend is present. As I start counting, I find that my friend is actually at the 100th house, okay. Also I note, if I come outside and I am looking at this one from here, this corresponds to the sense of right and this would be the left, okay. So I am actually looking, this is me who is looking, this is the eyes at which I am looking, and then you see that to this I have houses to the right and houses to the left, and at 100th house to the right is my friend's house, okay. So I pick up a phone and then say, well, you come out of the house, look to the left and then come to the 100th house. What would that person do? He would come out, or she would come out, your friend, and then they would look at their house. Their house will carry a number 0, and since it is to the left that has been mentioned, that person would walk all the way to your house, which corresponds to 100 left to that person, okay. So this way you have actually solved the problem. Otherwise you would never be able to invite your friends, nor you would be getting an invitation to your friend's house for lunch or a dinner. So this seems to be very simple way of representing locations, okay, by making one of them as a reference. Now it could be even made even more simpler. I know that there are only two directions here, right? It would be right or left directions, and every direction, right or left, there is a certain house along that direction, right? So I can begin to actually label this in a slightly different way. I call all houses to the right as plus and all houses to the left as minus, okay. So this immediately next house to me on the right side will be +1, and so on my friend's house, which is now +100. Similarly, the houses to the left will be -1 immediately, and then there is another house at -129, okay. So these numbers along with the sign would indicate particular locations, but there is nothing specific about having only houses. Let's say I have a chicken, okay, which can walk at any place, okay. This chicken can go along this road either to the right or to the left, and it can stop at any point and lay an egg on that. So if I want to describe the position of this egg, right, I cannot just say +1 +100, because this could be at at some unit distance 0.3 from 0. So I need to actually go to the real number system in order to specify every point on this long road, and I can do so by the simple number line arrangement that you are all familiar with. I call my house as a reference house, call it as 0, and then the increasing distances from my house will be measured by a real number. It's like a scale, and I am measuring that one by a real number. There will be some unit which I would have chosen. I could measure all my distances in terms of a meter, kilometer or centimeter and so on. No matter what unit of distance I choose, any point on to the right or on to the left can be specified by a real number. The only distinguishing point, so these 2 points are actually at the same distance, right? So these 2 points are at the same distance, but then they are separated or distinguished by the fact that one happens to be to the right of 0, the other happens to be to the left of 0. So this would be plus x0, this would be minus x0. Okay. Any point on the line can be specified by a single number. Let's call the point itself as p, and the value of x at that particular point will essentially be the coordinate or the location of this particular point. I can extend this idea of one dimensional coordinate system, that is on a road, to a plane. Okay. Imagine I want to, I am actually able to go everywhere on the plane, on a field or on a road that I am going. Then let's say my car is going around like this. I don't know whether this is a nice picture of a car, but let's assume that this is a car. Okay. The car could be traveling anywhere along the north direction, could be traveling along the east, could be traveling along the south, or could be traveling along the west. Okay. Now the car could also be traveling along northeast, or it could be traveling along southeast. Okay. Instead of talking about a north, east, west and south, I can go back to the number systems and then obtain a simpler representation of this. This is called as the Cartesian representation. I consider again any point on this infinitely spread over plane as a point 0 or the point origin. Okay. And if I move along this line, which is shown to be increasing along this way, if I move along this line, I am increasing the distances along this road, okay, which I will call as points x. Okay. So there is a label which I am going to make along x, and this would be the units which I am going to assume it to be the same units of distance for both x as well as another direction which I would call as y. Okay. Just these two directions are sufficient, because north would then happen to be plus y, okay, at a certain distance, south would happen to be minus along the y direction, east would happen to be plus or positive x, west would happen to be negative x. And if you want to specify northeast, you can specify this northeast by asking someone to move a certain distance along along east, and then move a certain distance towards east. What I have actually done is to create for every point, okay, two numbers which would be x and y, and this is also giving me an algorithm to move along and reach different points. I can move along one axis, as we would call it, this is the x axis, and then move along the y axis. Alternatively, I can move first along the y axis and then take a right turn, left turn, whatever the turn that I want to take, I can then move and approach the other point. The direction which I follow, the path which I follow, does not matter to the location. The location is fixed by the two numbers x and y that I provide. Of course, the origin will be denoted by 0 and 0. Okay. Again, you will notice that x itself can be positive and negative, y itself can be positive and negative. In the previous case, you just had one number which could be either positive or negative, which would be denoting this particular location of the house. Here now, to specify a location, you have chosen two numbers, and look at what you have chosen. You have two blue lines which we have drawn two arrows at the end. These arrows simply signify that they are increasing in this particular direction. But if I now stop at this red point, which was originally the red point, okay, and then draw one arrow and terminate it at this point which was the red point earlier, so call this point as some point P. Okay. If I draw an arrow from the origin and stop at this point, what I have done is to essentially describe a vector. Okay. Let's call this vector as vector OP, where O is the origin of the vector, P is the ending point of the vector. Okay. The length of this vector OP will be denoted by this, by putting the vector in between these parallel lines. Okay. And you can also notice that I can define a unit vector along the increasing direction towards x and a unit vector along the direction of y, and then I can describe OP vector as some alpha times the unit vector along OP, which I will call as OP hat. Okay. Of course, if I take, instead of OP, if I take x, or if I take the x axis itself, then I can define a unit vector along the x axis, which I will further denote as x hat. So here you can see that OP hat is essentially the same as the x hat that we are using, and these hat vectors are called as the unit vectors. So this is something that we already are familiar with. So the same grid that we had, which had north, south, southeast, east, northeast, west and so on, has been now mapped, as we would call, has now been mapped onto a two-dimensional grid in which you have placed x real numbers and real numbers y in the two increasing orders. You can also note one more thing. I have x hat vector. I can similarly define a y hat vector, which would be just one unit vector, that is the length of this vector would be just one unit, and it would begin at the origin and terminate it at one unit along the y axis. Okay, so just as x started at the origin and was terminated at one unit away from the origin along the x axis, I can do the same thing along the y axis. Then any point x and y can be associated with a vector which can be written as ax x hat plus ay y hat. What is this ax x hat and ay y hat? The point P, which was present at x comma y, okay, this gives you any point on the grid that we had considered. Then if I draw an arrow from the origin point all the way up to this point P, then I will be defining a vector which we can call as a vector OP, and this vector can be given in terms of, so how do I move in order to go from point O to point P? First I have to take ax units along the x axis, which is along this right direction or left direction depending on the sign of ax. So I move along this axis by an amount of ax. So by itself ax x hat is a vector whose magnitude is ax and angle is along x axis, right. So magnitude is of course magnitude of ax, it cannot be this one, and then I move either up or down. So I could move in any way I want, so I could move either up or down. If the point P happens to be located here, then I have to move a distance of ay and I would have arrived at point P. Although I actually started at origin O and arrived at point P, okay, I did so not by moving directly from O to P, I did so by moving along x and y, okay. But no matter what I did, whether I moved directly from O to P or I moved from ax and then moved to an intermediate point along x axis and from there I moved along to the y axis, I have arrived at the same point. So in fact, if I draw a line, which is the red line that we have drawn here, this corresponds to the actual vector because it has a origin here and it has a tail here, okay. You can see that this vector has been written as the sum of these two vectors, right. So this is geometrically how you add two vectors. You can take the first vector and to the tail of the first vector you put the head of the second vector, and then you draw from the head of the first vector to the tail of the second vector to geometrically complete this triangle, and you would obtain the sum of these two vectors. And if you now remove these ax and ay, this would simply be a vector that begins at the origin, which is described by the points or coordinates 0, 0 and terminates at P of x, y, right. So this is an example of a vector. The way this vector can be obtained is to add two vectors, okay. One vector will be along the x axis, ax x hat, ay y hat. What would be the length of this vector OP or the magnitude of the vector OP? The length of vector OP is very simple, right, and it can be related to this ax and ay. How so? I know Pythagoras theorem tells me that if I take this right angle triangle, then this distance that I have is equal to ax square plus ay square. Alternatively, the length OP of this vector, okay, is given by square root of ax square plus ay square. Finally, notice one thing. We had a vector along x axis which could be any vector, but for now consider the unit vector x, and then you had one more vector along y direction which was the unit vector y. So let's make it unit vectors here, it's not looking unit. So if I now make it into a unit vector, right, or consider two unit vectors, I see that geometrically they are meeting in such a way that the angle between them is 90 degrees, right. So these two vectors are called as orthogonal or perpendicular vectors. Okay, so these are perpendicular vectors. However, if I consider the vector OP, right, so this is the vector OP, this vector OP is not equal to the vector, let's call this as Q. Okay, so there is a vector OQ here and a vector QP here. So you can clearly see that OP is not perpendicular to OQ, or OQ is not perpendicular to, or rather sorry, QP is not perpendicular to OP. In fact, there is an angle between the two. And if you now imagine that someone is shining light from the top, you have actually constructed this one and someone is shining light onto the top, what would be the shadow cast by this line? That shadow will have a length given by this vector OQ. So you can imagine someone has a torch and then shining light onto this one, and you can immediately see that the length of the vector OP along this direction in which the light is shadowed, so which is along the direction x, will be exactly equal to the magnitude of the vector OQ. So in fact, in mathematics we can find out the vector or the length OQ by performing what is called as the dot product between the original vector OP and the vector OQ. Okay, so you can take any two vectors and perform a dot product, which is a result which will give you a number which is given by the length of OP multiplied by the length of OQ and cos theta, where theta is the angle between the two vectors. And in fact, what would be this length? This length we already have seen that it is equal to AX. So in fact, we can take the original vector OP equal to AX x hat plus AY y hat, and then dot this vector OP with x hat, okay, which would be a unit vector along which I am going to dot. Okay, and then I see that, and one thing that I forgot to mention is that it doesn't matter in which length you perform the dot operation. You can switch OQ and OP orders, doesn't matter. So I can either do x hat dot OP or OP dot x hat, I get the same result. So if I do this, or if I take the dot product on both sides, I know that this left hand side would be the component of OP along the x axis, okay, and this would be given by the component AX itself, because y and x are perpendicular to each other, and dot product will obviously be equal to 0 for this case, simply because the magnitude of y, magnitude of x are 1, but then the angle between the two is 90 degrees, which is cos pi by 2, therefore this is equal to 0. So this is a dot product which we will now use in the next module to go from one coordinate system to the other coordinate system. So I hope you have understood the two-dimensional Cartesian coordinate system, as this is called. We now move on to three-dimensional Cartesian coordinate system. In a three-dimensional Cartesian coordinate system, I imagine that I have three axes, x, y and z. Okay, so I have three axes over here, and any point P on this axis can be located by specifying three numbers x, y and z. As before, I still have a vector OP which can be written as some AX x hat plus AY y hat plus AZ z hat, and the length of OP, which is the vector length, is given by square root of AX square plus AY square plus AZ square. What are these AX, AY and AZ? These are the components of the vector OP along x and y direction. Okay, so if you go to this one and then see, this is the component that you would obtain as AY, this is the component AZ, and this is the component AX. So you move along AX, then move along the y direction by an amount of AY, and then go up to get to AZ, or if Z is negative, you go down. Okay, you can also see that this three-dimensional system that we have considered is actually created by three different planes, x equal to 0, y equal to 0 and z equal to 0. X equal to 0 plane is where you specify both y and z, y equal to 0 is the plane where you specify x and z equal to 0 is the plane where you specify x and y. Okay, we will talk more about all this coordinate system, and then we introduce other type of coordinate systems in the next module. Until then, thank you very much.